honored to be here. Thanks to the organizers for meeting up. I've enjoyed all the talk so far, and I can tell you, so when I was a grad student in going to these conferences, the best advice that one of the young faculty gave us at one of the conferences was, but this was on the first day of the conference, was just go out tonight. Like, don't go home after dinner, go out and meet people and talk to them, because these people around you, like you're meeting them, you're talking about math, and then you want to really become friends with them, like these people might become your collaborators. And it really does work like that. So my main collaborator, Kerry, maybe I'll get to talk about our work at the very end of the talk. Like, we definitely met at these conferences, and first we became friends and talked about other things and played mafia or whatnot, and then I think we're slowly talking about math and really getting along and enjoying talking to each other, and then in the end we ended up collaborating a lot. And I think a lot of these collaborations are formed in these places where you get to meet people and talk to them, and also you see who you get along with mathematically and personally. So meet people. Well, so now it's too late. So I'm glad that nobody gave me this advice yesterday, because then you'd probably not be here at my talk. But you still have a chance to talk to people, so don't be shy, meet people in the breaks. This is a great opportunity to make friends and talk to people about math, or just see what people are interested in, and then who knows, maybe it's something that you haven't thought about yet, but later on you're going to think about something and you get, oh, I remember this person I met at this conference is thinking about this, and then you can email them and start the conversation. Okay, so that's the advice. So I'll talk about, in this talk I want to give a very basic introduction to Algebraic K-theory and highlight the connections to other fields. So I'll try to be ambitious, and since this is a talk about algebra and geometry, I'm going to try to keep switching back and forth and giving connections to number theory and to geometric topology. So I'll keep switching, and they won't be related. So you can, if you're more interested in one than the other, you can maybe fall asleep for 5 minutes and then wake up again. But I'll start maybe. Okay, so the first part of the talk will be an introduction, sort of a historical introduction to Algebraic K-theory. So let me remind you somebody's question yesterday in Ravi Batil's talk about, so he talked about, so now maybe I'm also going to make some asides. I wasn't going to talk about topological K-theory initially, but in Ravi's talk you saw a lot of things connecting to that, so now I can go on some tangents just so that you see the connection. So unrelated, just remember that in this talk somebody asked about this z that showed up in this expression and where the z comes from. And Ravi told you it comes from rank of vector bundle, complex vector bundles. But then you might wonder, so why is it a z? The rank is a natural number, right? So we should, like, maybe you could explain an n, but why is it a z? How come we get negative numbers? So the main idea that I'm going to talk about first is the idea of group completion. But before, maybe let me just tell you in general that algebraic K-theory is a functor, or really a collection of functors from, okay, so let me first see this. So we're going to have groups for each I, functors to leading groups. And then the input can be a bunch of things. So starting with rings, spaces. So today I'll focus on rings and spaces as input, but you can have schemes and varieties and all sorts of categories as your input. Okay, so definition. Okay, so let me give you this really what's at the heart of algebraic K-theory, which is the idea of group completion. So if M is a commutative monoid, so this means that it satisfies, it's a set with an operation, and it satisfies all the axioms of an abelian group except inverses. Well, so then you can make it into an abelian group. So the group completion is, so what you want to do is just formally adjoin inverses. So let's see what we can take the free abelian group on the elements. And then we can mod out by the relation. So let me maybe put some brackets around them. So the class of M, so the element M class N, I want this to be the same with M plus N, where this is the element in my model. So I just want the operation to be the same, but now I have inverses. Yeah, so this is what's called group completion. And let's do an example. Okay, so what is the group completion of the natural numbers? Well, so this is how you get the integers. And now we're going to do something a little crazier. So for R a ring, we're going to define a group K naught of R to be the group completion of, so now our monoid is going to be isomorphous classes of finitely generated projective R modules. Okay, so this seems, it seems hard to wrap your head around. So now we have negative modules. So this is what Ravi was talking about in his talk yesterday too. So don't leave the room. I'm going to convince you that this is actually meaningful and it gives you interesting things. So the connection, so what he was talking about was more topological, but maybe as an aside, let me tell you, so before this definition came the definition of topological K-theory, and for space X, that was defined as the group completion of the monoid of vector bundles on X. So this was Ravi talked about in his talk. So I might come back to that later just to explain more how you get a Z times BU. Okay, so now maybe as an exercise, you can try to figure out why in this definition we need finitely generated. Okay, so maybe try to figure out, let me just give you a hint, so what would happen if you allowed for infinite dimensional modules. So suppose that you have some projective module, and now, okay, so maybe we can do this exercise together as a warm-up now, so that you see why we need a finiteness condition in the definition. So if I look at P plus R infinity, if I allow for infinitely dimensional modules, I could rewrite this as P plus Q plus P plus Q infinitely many times. So now I could associate this in this way, or I could associate this in the other way. And this is isomorphic to R infinity. Okay, so what does this mean? So this tells us that the class of P is 0 in algebraic K-theory. So this would mean that the whole group would be 0 unless we impose the finiteness condition like this one. Okay, so let me quickly do two examples. So we already know what the group completion of the natural numbers is. So we'll use that to compute K naught for F a field. Okay, so for a field, how do finitely generated projective modules look like? So they're all free, and so they're all F to the n. They're determined, so isomorphous classes are determined by just the dimension. So before group completing, that monoid is just n, the natural numbers. So the group completion is going to be Z. And similarly, if I take a PID from the structure theorem describing finitely generated modules over a PID, I get again that the monoid before group completion is n, and after group completing, I get Z. And so I think this microphone is, I'm not, oh, can you all hear me? Okay, so then we won't worry about it. Okay, do you guys have questions so far? So this is really the basic idea that's at the heart of algebraic K-theory. So now so if this makes sense, now I'll convince you. So before we move to further K groups, let me give you, so I said I'll give examples from number theory and examples from geometric topology. Okay, so now we're talking about K naught of a ring. So let's see how this is connected to number theory. So maybe I'll use colors. So what do number theories care about? So suppose you have a field extension of, a finite extension of Q, and then you have the ring of integers, usually denoted OK. And in number theory, you care about this ring of integers, and you care about the class group and the size of the class group and so on. So but this is the ring of interest. So let's see what K naught of OK is. So this is a ring of integers. Okay, so for this you have to know a few facts from that you learned in the basic number theory class, algebraic number theory. So one is that the ring of integers is a Dedekind domain, and then there's a similar structure theorem for finitely generated projective modules, like there is one for PIDs, there is one for Dedekind domains. And what it tells you is, again, that every finitely generated projective module here is determined, it has some free part, is determined by some integer, plus a uniquely determined ideal in the ideal class group. So this is what the structure theorem tells you. And now when you're group completing, so you still have this integer, you get n, this group completes to z, plus you get the ideal class group, and that's already a group. Okay, so this is how this shows up as K naught. The ideal class group shows up as K naught of number rings. Okay, and then let me give you an example from geometric topology. Oh, I cannot spell topology, that's really bad. Okay, so this is now going to be, so this was maybe an exercise that you could do. So this example is going to be a theorem, a hard theorem of walls. So if you have X, a path connected space, let's say of the homotopy type of a CW complex, and suppose that X is a retract of a finite CW complex. This is also called finitely dominated. You can ask the question, is X itself equivalent, so is it homotopy equivalent to a finite CW complex? This was a question of interest in geometric topology, so figuring out when a space was a finite CW complex. And so it turns out that there is a way to determine this using this group K naught. So the theorem, and of course there's lots of constructions involved that I can't tell you right now, is that there exists an element, it's called the wall finiteness obstruction. That lives in the reduced K naught of the group ring of pi 1 of X, so the fundamental group. So what is the reduced K naught? This is just the co-kernel of the map from Z to K naught. So this we can define for any ring. We can take n to the free module, the finitely generated free module of this ring. Okay, so there exists this element. You can define an element in here with a property that it is equal to 0. So, well, you can probably already guess the property from the name. So the wall finiteness obstruction. The wall comes because it was invented by Wall, and it's a finiteness obstruction because it vanishes exactly when X is a finite CW complex. Okay, so hopefully this convinces you that K0 has relations, so it relates back to algebraic number theory via the fact that if you look at the number ring, it's a class group, or class this X plus Z, and it was of great importance in geometric topology due to this theorem. Okay, so now let's move on and I'll talk about the next K group, which is K1. So it's going to be completely different definition. So a priori, these things would seem unrelated. So it's just going to be another definition of another invariant of a ring. So another group associated to a ring. But you can already guess from the name, so K0, K1, that these are going to fit in a sequence and they're going to be related in some way. Okay, so this was all K0. So now let's give another definition of another invariant. Okay, so K1 of R. So how do we define this? So this is going to be, again, a very, very hands-on algebraic definition. So we're going to take the general linear group of R mod the elementary matrices. Okay, so GLR is the co-limit, so the union of all the GLNR, all the finite ones. And ER is the subgroup generated by elementary matrices. Okay, so let's look again at some examples. Okay, so we all know linear algebra, so just if we're over a field, you can show that this is SLF, and then you get, so your quotient, this quotient becomes just the units in F. So for a field, again, this is an easy exercise to do. Okay, so now let's see what happens for other rings. So now let me tell you a theorem. Okay, so let's again go to the number theory. Oh, I was going to use different colors, but I guess I use green for both. Maybe we'll stick with that. Okay, so number theory example. So let's look again at OK. So let's have the ring of interest in number theory. So what happens if we compute K1 of OK? So this is not easy to see, but it's a theorem of Bass, Milner, and Serre that this again is the units of OK. So let's see, for Z, so that's an example of a number ring. For Z, you could still figure this out as an exercise because Z is a Euclidean domain and you can still do some linear algebra over it and show that the subgroup of elementary matrices is SLC and that you get the units. But in general, this is a hard, there's a lot more going on, so you have something to show. So maybe let me say in general, you always get the units plus something, which is the kernel of a determinate map. But this something doesn't always vanish. Okay, so now we have this, and now we can combine this with another theorem from algebraic number theory. So we have what's called the Dirichlet unit theorem, which tells you exactly what these units are. So it gives, and it tells you what the torsion part and what the free part of this group is. And the torsion part, we know that usually mu k. So this is the group of roots of 1 in OK. Plus, okay, so what is the free part? So it's going to be a bunch of z's. And okay, so these numbers R1 plus R2 minus 1. What do they mean? So R1 is the number of real embeddings of K, and R2 is the number of complex pairs of embeddings. Okay, so the point is that there is an explicit description of this. Okay, so for now, so we'll come back to this. So for now, maybe just keep in your head, remember the things that show up in here. So there's the group of units, and then there's these numbers R1 and R2 that count embeddings of K. And well, they will show up later, so maybe let me give you a minute to just let it sink in, and then hopefully you'll remember when you see them again and you'll be able to recognize them. Okay, so now let's switch gears and give an example from geometric topology again. About how K1 of a ring shows up. So again, it's going to show up in a very significant way. And I'm going to state another very, very, well, maybe a few combined theorems of great significance that are going to be described in terms of K1 of, again, the ring in question is going to be the group ring of pi 1. So let me start with a question. So in geometric topology, suppose that you have two manifolds that are homotopy equivalent, that are smooth and dimensional. So you can ask, is M diffeomorphic to N? Okay, so how do you answer this question? Okay, so the approach is you can build something called an H-cobordis between them. So let me start with the definition. An H-cobordis W between M and N is an n+1 dimensional manifold such that, so there's two conditions. The first one is the condition of a cobordis. So if you have seen this, so the boundary of W is required to be M disjoint union N. And the other condition is that makes it an H-cobordis is that the inclusion of these boundary pieces are homotopy equivalences. Okay, so if you've seen cobordis before, you have probably seen this example of the pair of pants. Has everybody seen this? So this is an example of a cobordis. It's not an H-cobordis, right? Because a circle is not homotopy equivalent to two circles. So this is not an example of an H-cobordis. This is a cobordis, not an H-cobordis. So what is an example? So an example for sure is the trivial H-cobordis. And you can ask, so given some other H-cobordis W, you can ask, and maybe W looks crazier and it's not clear if it's diffeomorphic to the trivial one, you can ask the question, is it diffeomorphic to the trivial one? And if it is, then you get that M is diffeomorphic to N. Okay, so maybe I can get this here. So now the big theorem for which we're going to need K1 is, so I'm going to combine the statements of the H-cobordis theorem of Smale, which you want the Fields medal for in part, and the S-cobordis. So this is a generalization of the H-cobordis theorem. S-cobordis by Garden, Maser, and Stallings. Okay, so what it says is, so we need the dimension of M to be at least 5. And what it says is, so we want an obstruction where we want to know when an H-cobordis is trivial in order to answer this question. So what this theorem tells us is that diffeomorphous classes of H coordinates on M are in one-to-one correspondence with elements of a group. So this is called the Whitehead group of phi1 of M, and this group is defined to be, so this is going to be a quotient of K1. So K1 of the group ring mod plus minus the elements in pi1 of M. Okay, so let's see, so let's recover. So Smale's result was just for the simply connected case. So it told us that in the simply connected space, every H coordinate was trivial. So if in the simply connected space, if pi1 of M is trivial, so let's see if we can recover it. So let's try to compute this Whitehead group. So the Whitehead group in this case, okay, so Whitehead group is going to be K1 of Z plus minus 1. So now we can go back. Well, we already have this stronger theorem that told us that K1 of OK for every number ring is the units. So in particular for Z, so as I said, this you could figure out even without that theorem, just Z. So if you're going to get the units, mod plus minus 1. So indeed, we're going to get that it's trivial. So in the simply connected case, it says that every H coordinate is trivial. And so this was Smale's result. And in general, to every H coordinate, you can associate an element called the Whitehead torsion in here, and your H coordinate is trivial precisely when that element vanishes. So it's more precise than this. So you have an obstruction, just like the Wolff-Heinemann obstruction. You can build an element in here and plus minus the elements of pi1 of M. Right, so you can view those as elements in there. Okay, so now, do you guys have other questions about this? Okay, so far I gave two definitions, right, seemingly unrelated, of what we call K0 of a ring and K1 of a ring. And there was also a definition of K2 of a ring, very explicit algebraic definition. So I'm going to skip that for now. But so these three definitions preceded the definitions of higher K-theory, and it turns out they were connected. So there are theorems about K0, K1, and K2. So they fit together in some sequences. There's things connecting them, and the big goal was, at the time, was to try to generalize these definitions, to come up with a definition of higher K groups that recovers the existing ones and also generalizes all the theorems that existed about them. And okay, so let me first say that these are very difficult to construct. So Quillen was the one, and there were approaches before, and in particular there is a very relevant definition of Milner also for fields of higher K group that's different, but Quillen was the one who gave the definition of what are now called higher algebraic K-theory for rings. So Quillen defined Ki of R for all I. So of course it recovers K0, K1, and K2, and it extended the results connecting these. And there's expected results like long exact sequences of K groups that you'd expect of the right definitions and so on that Quillen proved. So let me just tell you this first about the definition. So these are going to be functors from rings to abelian groups. And the way they are defined is they are defined as homotopy groups of a certain space. So he defined a functor to, so for now let's say spaces, and then you can take the homotopy groups. But these are not just spaces, so the space, the algebraic K-theory space, so this functor actually lands in very special kind of spaces. So let me maybe put in brackets here, infinite loop. So these are what are called infinite loop spaces, which means, so for, I don't know how many algebraic topologists, homotopy theories are here, right? So these are what homotopy theories called spectra. So they correspond to spectra. So these correspond to generalized cohomology theories. So there's all sorts of going back and forth these concepts. But well, by the name you can guess what an infinite loop space is. So you have the space, so the K-theory space has the property that, so we saw yesterday in Ravi-Stock loops, right? So this is going to be loops on something, but furthermore it's going to be equivalent to loops 2 on something else. And then, so x1 itself is going to be loops on something, and so on forever. Okay, so a loop space is already a crazy space that you cannot quite imagine, right? A space of all loops in a base loops in a space. So now you have loops, and then you have loops on loops, and then you have loops on loops on loops. So, well, this should tell you at least that this is a very hard, complicated space. But also it has very nice properties because this gives you a lot of very nice structure. So let me tell you a little bit about how KR is constructed. So this is going to be, let's maybe write GR top, a topological group completion. So before we talked about just group completion of an algebraic monoid, but it turns out you can do a construction on a space. So a monoid was a set with an operation, with a commutative operation. If you have a space that has an operation on it, it's only homotopy commutative and homotopy associative, and so on. You can do a topological construction to it to make it into a space where you now also have inverses up to homotopy. And well, one of the pioneers, Lusa, the group completion theorem that gives a model for the group completion of a topological monoid is due to Lusa, McDuff, and Siegel. So there are nice theorems and models for the group completion. So for now, I'm not going to tell you. Let me tell you. So all that I will tell you is what it does on phi naught. So this is going to be some group completion of some space. But now, what is the space? So this is also hard. You need hard constructions to get the space that you want to group complete. So this is going to be. So let me write it in words. The classifying space of the category of finitely generated, so, or let me write, okay, so the category, let's give it a name, ISO PR, let me make it bold to distinguish it from the PR from before, which it will be related to, of course. So the objects here are finitely generated projective R modules. And the morphisms here, we're just going to take the isomorphism between these. Okay, so now what is the classifying space of the category? Okay, so let me just give you a recipe for how starting with a category. So a category has objects and morphisms, so you can view it as a big or it can be a small diagram in your head, where you have your objects and then you have arrows between them, and arrows need to compose, and you have identity arrows. So how can we associate a space to a category? So the recipe is as follows. So the zero cells, we're going to build, you can think of a CW complex where the zero cells are going to be the objects, and the one cells are going to be so they're going to correspond to morphisms, and how are we going to attach them to the zero cells, where it will be attached by source and target. Okay, so let me draw a picture. So let's suppose that we have that this is an object, and this is an object, and this is an object, and here we have F and G. Okay, so in the picture, it's not the directions are not going to matter anymore. So suppose you have some arrow like this and some arrow like this. We're just gonna glue a one simplex. So suppose that these A, B, C were so these dots are objects in your category. If we have a morphist, two morphists that compose. So let me do three morphisms. Okay. For now, maybe let me do one morphism. So I only talked about one cells. So now two cells. Sorry, I was jumping ahead. Okay, so one cells we have for any two objects. I'm going to attach all the morphisms. The two cells. So now I'm going to attach. So instead of writing it down, let me just maybe draw it in the picture. And then the three cells and so on is going to be. It's going to be the same idea. So I will draw as much as I can. So up to three. Okay, so suppose that now, so this was one morphism that I glued in this one simplex. Now suppose I have another morphism G from this object to this object. So I'm also going to glue that in, but now these two morphisms compose. So if I had a morphism like this in my category, then I have the composite HG. Okay, so this also needs to be glued in here because it's a morphism in the category. But for every, so two cells are going to correspond to, so for every pair of composable morphisms, I'm going to put in these two cells. So now I'm going to glue in the two simplex. Okay, so now for three simplexes, so suppose now I have three composable morphisms. So one, two, and another one that composes. So let's say this was F, G. So now suppose I also have an H. Okay, so now, let's see. So I have this morphism that goes in, and I have this morphism that goes in. And this is H, G, F, the composite of all three of them. Right, so this is H, G. So I think I've labeled all of them now. So each one, so all the simplexes here, the two simplexes are glued in because they all correspond to composing two morphisms. But now because this corresponds to a composition of three things, I'm also going to glue in that three simplex. So this tetrahedron is going to be glued in there. And so on. And I cannot draw it anymore, but this is how you build all your n simplices. And then you have to collapse some things where you have identities. So let me not dwell on that. Okay, so maybe let's do a very easy example. So if you have taken algebraic topology, you have learned about CW complexes, you have constructed RP infinity at some point. So has everybody constructed RP infinity as a CW complex? Well, if not, we're going to do it right now. But I think, well, if you've seen it, then this is definitely going to ring a bell. So let's suppose that C is the category, so very simple category with only one object and one identity morphism which squares to the identity. So two morphisms, the identity morphism, and then one other non-identity one. That if you compose it twice, you get the identity. So in other words, if you think about the group Z2 as a category, this is how we think about it. One object and then the elements of Z2 are your morphisms. Okay, so now what is the classifying space of this? So let's see. So we're going to have an n cell for every n, and it's going to be attached to an n minus 1 cell by a map of degree 2. So if you look at just at the n skeleton, it's going to be exactly RPN, the way you build it. And so the whole thing is going to be RP. That's maybe right, almost the equivalent. So you can think about this more and follow the recipe and then convince yourself that you get RP infinity. Okay, so now So now we have some idea of how to build a space from a category. Right, so this is already an infinite big space, right? And this was a classifying space of one of the simplest categories that you can think of, just one object and one non-identity morphism. So you can imagine that when you have pretty big categories, and very big, so we still only want to do this for categories that have a set of objects that are called small, but those are still big in terms of how many objects and how many morphisms they have. So of course this is going to be a very complicated space. So the space that we're considering is the classifying space of the category, we said, of finitely generated projective modules. So let me tell you this about the group completion. So pi naught of the group completion, this topological group completion of a space. So in this case, our space is this classifying space. But so in general, if you have a space with an operation, it's pi naught with a homotopy commutative operation. Its pi naught is going to be a commutative monoid. So we can talk about the group completion just of a monoid, like we did on the very first board, just for its pi naught. So the property of the group completion on pi naught, and this is what it wants to do. So if the purpose is to group complete pi naught. So on pi naught, it will be the the algebraic, so just the group completion of an algebraic monoid, which is pi naught of your space. So the space that you do completing always has to have some operation, some homotopy commutative operation. So then it makes sense to, so its pi naught is going to be an abelian monoid, but it might not be a group. Okay, so now we know on pi naught what the group completion at the topological level does. So let's try to see if we recover our old definition of K naught. Okay, so I think we understand the classifying space enough to compute the pi naught. So let's try to do that. Okay, so what is pi naught in this classifying space? So we said that the zero cells, right, are going to be, well, I cannot draw some, well, there's of course infinitely many modules, but so that all we have to figure out is what the path components are. Right, so we have a bunch of modules, and when do you have a path between them? Well, our morphisms are only the isomorphisms, right? So you're going to have a path exactly when you have an isomorphism. So the ones that are going to be in the same path component in this space are exactly the ones that are isomorphic to each other. So this pi naught, okay, so I said I was going to make this bold to distinguish it from the PR that I wrote over there, which was just with this monoid. Okay, so suppose this is bold. So this is exactly the PR from before, which was, right, so it was the monoid of isomorphous classes of finitely generated projective modules. So the ones that are in the same isomorphous class are going to form a component. And the components are going to be the isomorphous classes. So on pi naught, this is what's happening. Okay, so do you guys have questions up to here? So at least. Well, they're going to be all in the same component, right? So they're not identified, but in pi naught they're identified. Right, so in pi naught, so this is what a path means.
I guess like the morphisms are isomorphisms, like isomorphisms between the modules, right? So in the previous time, very well that. Yeah, up there, right? Those morphisms are just isomorphisms?
No, not necessarily. So here I'm trying to give the general recipe for any category. So no matter what morphisms you have, right? So no matter what morphisms you have isomorphous or not, you can follow this recipe, right, and just see how they compose.
Yeah. Yeah, it's just like more equals iso, right?
Oh, yeah, sorry. So maybe this is confusing. So this was unrelated to this part, which was more general.
Okay, yeah, sorry.
Yeah, sorry about it. Sorry. So this was just a definition of this category.
All right, that's all right.
Okay. Yeah, sorry about that. So the definition of this category, I could have like not taken this, and that's also like a fun category if you think of this classified space.
Yeah, sorry.
But when we want to do K-theory, we take the category of isomorphisms. So this recipe works in general, and then so the gluing relations are dictated by composition of morphisms. But maybe now that you ask, I can say that well, a lot of the times. For example, if you have an initial or a terminal object in your category, your classifying space will turn out to be contractible. You can build a contraction with that object. So many times, like your category the classifying space might not be interesting. But in this case, right, it is. Okay, so in the remaining time, so now I told you that there's a complicated space that you can construct. Right, that's the K-theory space. Okay, I can still read those boards. So you know what? Let's leave. Okay, so maybe I'm going to leave. So let's leave this. I think we can. I don't think we need this anymore. So now let me go here and. Right, so now the big question is, why would we care about this? Why would you want to construct something complicated that is clearly hard to compute? And the question, and well, the answer again is because the higher K groups are going to have very interesting connections to number theory, to geometric topology, and to lots of other, to algebraic geometry and so on. So let me give you some of these examples. So let me start with number theory. And also, what time did we start? Okay, thanks. Okay, so in the last 10 minutes, let me give you these examples, and then maybe at the end I'll talk a little bit about what I'm thinking about at the moment. Okay, so in number theory, there's the class number formula that you learn in a first class, maybe on algebraic number theory. So it's a formula that combines a lot of these numbers that we have seen into one very amazing formula. So I will give you the analytic version, which maybe it's a little harder to motivate. So the classical version is just the formula for the pole of the zeta function at s equals 1, and then via a functional equation you can translate it into this other form that's called the analytic form. But this is the one that's going to be more relevant to us. So it says that the limit of the zeta function, so we're again in the same scenario where we have a field extension k. So this over s to the r1 plus r2 minus 1 is equal to, okay, so this is the class number. So minus the class number times the regulator. Okay, so maybe you can ignore the regulator since it doesn't connect with what we've seen. But the class number, so let me say this is the size of the class group. And then the denominator, so what's called omega, usually this is the number of roots of 1 in k. So it's the size of this mu k. Okay, so now, okay, so it's great. We still have this and we still have this. So now you can just stare at this and see that in this formula, right, so in this formula for the class number formula. Okay, which numbers do we recognize? Okay, so we recognize this, and this is exactly the rank of K1 of OK. And we recognize this, and this is exactly the torsion of K1 of OK. And the size, and then we recognize this, and this is exactly K0 of OK torsion. Okay, and then you might be ambitious and make a conjecture. So Lincoln-bound conjecture, a generalization of this class number formula that says that the limit as s goes to minus m so I'm just going to replace these things that we have recognized with ranks of higher k groups, k2m plus 1 of OK, and well, this is all, it was unclear if it's like up to a constant. So then the size of k2m of OK, and the size of k2m plus 1 of OK torsion. Oh, times well, you still need some regulator. So times some higher regulator. So it appears, from what I understand, that this conjecture is now proved, that it follows from other work that has been done. But if you want the conjecture, so well, this should seem amazing, right? That you take this very classical formula in number theory, and you recognize sizes of K0 and K1, and then you can generalize it in the sizes of higher K groups, give you a generalization of this. So it should be mind-blowing. Okay, so maybe just, I will leave this on the board. So this was K1 and that was K0 of OK. And so quickly before we go back to topology, let me say that, so another conjecture, so the Kummer, so this one is still open. So one of you can prove it, maybe. So the Kummer-Van Diver conjecture, so this is a conjecture again purely number theory, so the way I will state it. So it says that P does not divide the class number of Q zeta P plus zeta P inverse. So this is the maximal real subfield of Q zeta P. So this is a conjecture of great importance in number theory, and as far as computers can compute, so for P high enough that computers can compute, it's true, but of course the counterexample would be very big, for P very big if it existed. Okay, so this conjecture is still open, and then the crazy thing is that this is equivalent to K for I of Z being 0 for all I, which also means that K of Z is not known. Okay, so you can think about it. So that's like really mind-blowing connection, and it means that if you could compute K of Z, it would have this great implication in number theory. Okay, so now let me. So if you don't care about number theory and you don't like that, so let me switch gears again, and in the last 5 minutes talk about geometric topology. And so now Waldhausen extended the definition of K-theory to take as input spaces. So now, just because to avoid the confusion with topological K-theory that I mentioned, it was defined in terms of vector bundles, so that K of X, we're good. This is now called A-theory, so it's still algebraic K-theory, but for spaces. So again, we have functors like this, and there is an A-theory space, so this again lands in infinite loop spaces. And so for every space X, there is another space A of X, which is its K-theory space or its A-theory space. And so the amazing theorem, and the reason why Waldhausen did all the work of extending the definition and building all the necessary machinery to do so was to prove this, or to state this theorem, which, so all the details of which were proved much later in recent work with Yaren and Rogness. And Hatcher has done a lot of work on this and at some point had claimed the proof. So the theorem is that this A-theory space decomposes as, so something, I'll call this loop infinity, sigma infinity x plus. So it looks scary, but this is just a stable homotopy of x. So it's the space whose homotopy groups are the stable homotopy groups of x times another space such that, so when M is a smooth compact manifold, loops on this Whitehead space of M is a space, is going to be a space of H cobordisms. So this is going to be a stable space of H cobordisms with, so if we look back at it's just its path components like we did before, this is just the Whitehead group of pi 1 of x. So the Whitehead group that we have encountered before. So okay, so now maybe in the last 2 minutes, since I don't have more time, I'll tell you about the project that I'm thinking about with Kerry, which is, so now, well, joint with Malkiewicz is trying to suppose that you have a smooth compact manifold, but it has a G action. So now we can try to think, well, is there a definition of an equivariant version of A-theory in such a way that it splits as an equivariant stable homotopy theory times some factor which is related to equivariant H cobordisms. So we saw, so before we saw the definition of an H cobordism. So if you have group actions everywhere, smooth actions everywhere, so well, it would be equivariant if these maps are G homotopy equivalences. So you can ask the same question: is W now G diffeomorphic to M times I if M has a G action? So it's exactly the same question as before. And there's versions of this, like what would be the pi naught statement of something like this, just about equivariant Whitehead group that we're trying to generalize to the space level. Okay, so in the last minute, maybe let me make a philosophical remark, like in Ravi's talk. So this is really all still modular spaces. Okay, so we have, so in the past, people were working and studying these sets, maybe sets with operations, groups, and now we're making a whole space that has a lot more structure. It's a space or a spectrum in the sense that I said, but when you take its set of connected components, you get back these classical groups. But now these spaces, right, like this space of H cobordisms, have a lot more structure and information that lets you compute other things. So it's a lot richer than just its pi naught, which is already this group that's very interesting that we're trying to generalize. And equivariantly, things get a lot more complicated. Let me just say this, because so it's not as simple as just keeping track of the group actions, but in the stable homotopy theory, there's all the group representations of your group that come in, that are built in, that you have to take into account. And the stabilization, so here I didn't say exactly what it means. It's with respect to intervals. In the equivariant case, it would be with respect to representation disks, so disks in a space with a group action, in a vector space with a group action on it. So that's what makes it a lot harder. Okay, let me just end here. Okay, so it turns out, so what we have shown, right, so here in this question, so this is the only thing that was known, right, so equivariant stable homotopy of G space, right, so this is known, the suspension G spectrum. So we have to define this and this such that we have these relationships. So what we have shown is that, and as I said, so there's something else that we have to connect it to, because we want to connect it back to this, and as I said, there was a known definition of just the equivariant Whitehead group. And it turns out that this equivariant Whitehead group, in previous work by Paul and lots of other people in the 80s, so it's shown to satisfy a lot of these properties and encode an obstruction, and it has a splitting over conjugacy classes into terms, well, into some non-equivariant terms. So this is how, okay, so in general, this AG of X, so it's fixed points, so, and let me just tell you what the fixed points are going to have a splitting, let me write it as a product, over conjugacy classes of subgroups into non-equivariant terms. And the non-equivariant terms are, so the fixed points, and then I'm going to put the H for homotopy orbits. Okay, so what still acts on the fixed points? So the fixed points don't have a G action anymore, right? But they have a WH action where this is the normalizer of H. Yes, sorry. So this would be G mod H in the case where if your subgroup is normal, otherwise it's a normalizer of H mod H. Okay, so now let's see what this would be. Okay, and what is this H? So this is what Ravi talked about in his talk. It's homotopy orbits. So homotopy orbits means, so let me just write in general. This is, okay, so now let's answer your question. So for C2, and let's maybe make it very easy and suppose that X is a point and look at the fixed points, C2 fixed points in the case of a point. Right, so now we can analyze these terms, right? So we proved that like there is this definition and it has the splitting of fixed points. Okay, so if it's a point, we're doing like the quotient that Ravi is talking about, homotopy quotient by C2, which is just BC2. Oh, and we just computed BC2 somewhere, well, I erased it. Right, so BC2, it was just RP infinity. So what we're going to get is A of a point is going to be one term, and A of RP infinity is going to be the other factor in the fixed points of A, C2 of a point. So this is already, so this is already hard. So even non-equivariancy, so A of a point is already a very hard, so that's the same with the K-theory of the sphere spectrum. If you do K-theory for rings that are homotopical, so rings in spectra. And so that's already not fully known and a hard thing to study. But yes, so this is sort of what we can say. In terms of the fixed points, we have this decomposition and analyze it in terms of the non-equivariant pieces. Okay, but now what's the upshot? The upshot is that, right, so why would we care? So again, we're making things more complicated. But so before, right, we had functors to abelian groups. So now KG, so from spaces, and we can do this for rings also. So we have these functors, AG, KG, right, to what are now called infinite loop G spaces. And again, we're taking homotopy groups. Okay, but now the homotopy groups are not just going to be abelian groups. They're going to be what are called Mackey functors, which are systems of abelian groups. So we have one abelian group for each fixed point, and they're connected by transfer and restriction maps. So I only told you, right, you asked about C2, I told you the C2 fixed points. We also have the E fixed points. So we have two fixed points, but they're related by transfer and restriction maps. So that's the extra structure that we get that we could try to use. So yeah, I don't know how much this answers your question, but I don't think we can say much more. Like if we knew what it is, or not even non-equivariantly, we don't know what those things are, but this just adds extra structure. Or we know enough maybe for some simple computations, but so, well, I think this is as much answer that we know.
How does the Algebraic K-theory work, like groups and sort of natural actions, like a SOS?
Oh, I should have said, so for at least this last part, when I talked about equivariant case and what we're thinking about, G needs to be finite. Not because, it would be very interesting in terms of the group actions possible, but the machinery, the equivariant stable homotopy theory machinery that we're using, unfortunately only works with G finite. And it's just impossibly hard, and I think nobody at the moment knows how to do. Yeah, so that's another, well, I didn't talk very much in this talk about equivariant stable homotopy theory, but that's really what I'm doing, and it's a huge open question to figure some things out for compact Lie groups. Yes. It's a hard question. It's still like some of the things involved, like finding these deloopings for a space and